Hello everyone, this is Frank. Welcome to the third lecture of Anatomy of Pytorch XLA. In this lecture, we will take a closer look at XLA computation graph compilation and execution. Without further ado, let's move to our today's lecture. Let's make a quick recap of our last lecture. In last lecture, we saw how Pytorch XLA uses lazy tensor and tracing mechanism to intercept Pytorch operations and dynamically build a computation graph without executing the math immediately. We also saw that the sync function signals the end of the graph segment and triggers the next step, which is the compilation and execution. In today's lecture, we will explore how Pytorch XLA transforms the tensor and the computation defined in Pytorch through multi-layers of transformations. This is going to be a long lecture, and it touches the core of Pytorch XLA. In this lecture, we will center our discussion on 5 key components that appear along this transformation path. We will see atom Pytorch integration, XLA tensor, XLA node, XLA option, and XLA computation. We will start with a high-level overview that builds a conceptual model, then deep dive into each entity, what it is, what it does, and how it cooperates with others to achieve the end-to-end compilation and execution. In addition to the slides, I also draw a diagram with those 5 key components and their interactions. I hope this can help you to have a better conceptual model about how those key components interact with each other. So here, as you can see, we have a Pytorch integration, we have a XLA node, on the other side, we have XLA tensor, we have XLA operations, and we have XLA components. Those 5 key components are connected and interact with some helper functions and classes. So the first entity that I want to introduce is XLA tensor. So what is XLA tensor? XLA tensor is a variant of regular Pytorch tensor. The most important feature of it is that it can hold both an IR value and a device buffer. A device buffer is just another way to say a real value on XLA device. As we can see here in our graph, an XLA tensor contains 2 parts. One is the current IR value, another one is the device buffer. The device buffer represents the real value, and the current value, which is the IR value, represents an operation. Then we have XLA node. XLA node represents the input of the operation and the shape of the input. In addition, it also contains lowering function, which transforms the operation represented by the node to a more general and standard IR. The concept of this operation node is provided by Pytorch and implemented by Pytorch XLA package. In our graph, we can see XLA node is defined right here. It contains operation cans, operands, and the lower function. So the whole node actually represents an operation, and its attribute defines what operands that it takes and how we transform this operation to a more general intermediate representation. And we can see that the XLA node is actually stored as the current value in XLA tensor. Remember that in XLA tensor, it stores a value or a computation. And this XLA node actually represents a computation that you can get a value. So XLA tensor is just like a larger container. It's more general. It contains value or the way that to get a value. And the XLA node represents a way or a computation that you can get the value after the computation. Third, we have atom Pytorch integration. So this component contains many classes and utility functions. It's a glue that intercepts standard Pytorch tensor and operations and route them to XLA. Conceptually, it does 2 things. For tensor, it's usually convert a regular Pytorch tensor via XLA tensor creation method, so that a regular Pytorch tensor can be converted to XLA tensor that can hold both value and operation. For Pytorch operations, we have Pytorch dispatch mechanism that allow us to intercept the regular Pytorch operation. Through this mechanism, Pytorch XLA implements XLA native functions, which is a huge set of kernels that create XLA nodes for every Pytorch operation. For example, addition or multiplication. In the example of C equals A plus B, you write this statement in Python Pytorch. When the Python compiler executes this line, the A10 dispatch mechanism kicked in. A and B are converted to XLA tensor through the creation function. Addition operation is routed to XLA native function addition, which is the XLA version of the addition. Instead of immediately compute the result, it creates an XLA node that represents addition operation and captures the operand. Variable C, which is another XLA tensor, will be created at the end to hold the result of A plus B, which will be an XLA node. In the graph, this part represents A10 Pytorch integration. We can see its primary contains two parts. The Pytorch tensor are transformed through this create function to XLA tensor. And the Pytorch operations are handled through A10 dispatch and bridge mechanism. The operations and operands are recorded and eventually transformed and stored in XLA node. The result XLA node can be stored to another XLA tensor, which was C in our last example. Fourth, we have XLA operation. It is an entity that is produced from XLA node lower function and used to generate the final IR. Remember that XLA node represents an operation. It contains a lower function that is used to generate XLA operation. During the graph generation phase, the XLA engine reversely traverses the node in post order and call each XLA node's lower function to emit a set of XLA operations. And those operations are used to generate HLO, which is high-level optimizer. The HLO is the final IR that will be sent to XLA engine for final compilation and optimization. In our diagram, we can see here, from XLA node, once we reach the sync boundary, the XLA graph executor will use lower context to traverse all the XLA node in a reverse order. And through the lower function, it generates a bunch of XLA operation. And each operation contains a builder and parameters, which represents the input. The set of generated XLA operations are compiled to HLO, which will be sent to computation client and to generate the final XLA computation graph. Finally, we have XLA computation. It's an executable. It represents a compiled device executable that's generated by the XLA compiler. As I just mentioned, Pytorch XLA submits the HLO to XLA for compilation. It caches the executables and then executed with the device buffer as the input and produce the output and send the output to the device buffer. Remember that we get a bunch of XLA operations. Those operations are compiled to HLO, and HLO is sent to this computation client, which will send the computation build request to build the XLA computation. So the XLA computation represents an executable that can be run on the XLA device. Now we have went through all the major components in our graph. Let's take a closer look at those orchestration components, the XLA graph executor, lowering context, and computation client. Those things cannot be classified in any of those key components, but they play an important role in the whole process. So I think it's worth spending some time to introduce them as well. So first, we have XLA graph executor. It registers tensors and tracks them. It collects IR roots at sync and run the post-order traversal, manages the graph hashing, caching, and triggers the lowering. It's an overall orchestrator for the whole process. From the diagram, we can see that XLA executor has two routes. The first route is the lower route. It builds and compiles the computation graph. It eventually will contact with this computation client and build the XLA computation. The second route is the upper route. It has the XLA computation and instruct the computation client to execute the computation. So it's the center of building and executing XLA computation graph. The next important entity is lowering context. It's a context object created to translate IR nodes into HLO operations. It maintains a mapping from XLA node to XLA operations. It ensures that each node is lowered once and collects the output and input list in a deterministic order. In our graph, the lowering context is right here. It's used by XLA graph executor to build the computation graph and used by the XLA operations. It provides a context for translating those XLA operations to final HLO operations. It's an important object that you cannot miss if you have ever took a look at the lowering functions. Next, we have a computation client. It's an abstraction over the XLA runtime. Please don't be confused the XLA with Pytorch XLA. XLA is another package that is dedicated for transforming and optimizing your computation graph. Pytorch XLA is actually a bridge between Pytorch and XLA package. The computation client is the client that Pytorch XLA talk to XLA runtime. It accepts HLO and instruct XLA runtime to perform various of optimization and transformation. In our graph, computation client is right here. It's a bridge to talk with XLA device and XLA runtime. Now, you should have an overview about how Pytorch XLA graph compilation and execution works. Let's go through the whole process with more details through an example. This example contains 5 lines of code, as you can see from the slides. The first 3 lines create an XLA tensor. The fourth line adds 1 to that tensor and create Y. The last line triggers the computation graph compilation and execution. It's the simplest example that I can think of to demonstrate the whole process. I also create a sequence diagram for us to have a better visualization about the whole process. This is a sequence diagram that I created to demonstrate the execution of our example program. As you can see, it contains 3 main steps. The first step is to create host tensor and move to XLA. The second step is to execute y equals x plus 1 and build the intermediate representation. The third step is to start the syncing process and start to collect the root, do the lowering transformation, compile the graph, and execute it. Let's start with our first step. This step includes the first 3 lines of the code. It ends with the creation of the variable x. From here, we can see the first step, user create a tensor and initiate the move to XLA device. The initiated request is dispatched through A10 dispatch, which will be received by A10 XLA type.cpp. From A10 XLA type.cpp, it will call the XLA tensor create method, which will create XLA tensor. Third, the created tensor will be registered to the XLA graph executor. The executor will dedicate this registration to device context arena. After the registration, the created XLA tensor will be tracked by this device context arena. This completes the creation of the XLA tensor. The process that I just showed from the sequence diagram involves some concepts that I didn't introduce in the overview section. Let me briefly introduce them now. So first is XLA native function header file, a10xla type.cpp file, as well as the tensor method.cpp file. XLA native function header file and a10xla type.cpp file are the entry points of Pytorch to the Pytorch XLA world. They contain the manually written lowerings to XLA for each operator. XLA native function header file is auto-generated. It utilizes the code generation mechanism used by Pytorch. It contains the declarations for kernels that need to be defined in a10xla type.cpp. When you call .to method on a regular CPU tensor, the a10 library uses a dispatch mechanism to call the Pytorch XLA backend. This will actually involve a toCopy function, which is defined in a10xla type.cpp. That function delegates to another function called bridge create XLA tensor, which calls the XLA tensor create method to actually create the XLA tensor. The call chain on the second bullet point describes you how a to method on a regular Pytorch tensor can finally lead to the call to create an XLA tensor. There is an important process that I didn't mention in the overview. That is the tensor registration. Why do we need to register a tensor to the graph executor? The registration gives the XLA graph executor a per device index of what XLA tensor is available. When an XLA tensor is created, XLA graph executor registered its data into device context arena for that device. And this process built a fast map of device to tensor relationship. Some workflows need to know the tensors by device. For example, sync all the tensors on device XLA 0. Most of the debugging and dumping operations also need to know all the tensors that's managed by an XLA device. The registry is how the executor can enumerate them. Think of the device context arena as a per-device phone book of weak reference to XLA tensors. Register on create and unregister on destroy. The executor uses this phone book to coordinate sync debugging without owning the tensor or forcing the execution. So that's the first step. We created a regular tensor and transform it to XLA tensor. Let's go back to our diagram. In the second step, we're going to build our computation graph by recording the operations and the operands. Continue our journey, the fifth step, x plus 1, is called. This Pytorch code will trigger the dispatch mechanism, and the dispatch mechanism will enter the Pytorch XLA world through this a10 XLA type file. Remember that when we create the XLA node, we need to provide both the operation and the operand. So the next step, it recognizes that one of the operand is a constant. This will trigger the tensor method to create an IR value for that constant scalar. And this creation is actually managed by XLA graph executor. Then it will take just the created constant scalar IR and the input, which is x, with the operation kind, which is addition, to create an XLA node. Now the XLA node contains the operation can and the operands. This XLA node will be used to create a new XLA tensor that contains a pointer to this XLA node. And this newly created XLA tensor on the 10th step will be assigned to tensor y. So now we have complete the assignment of tensor y. Now Y is an XLA tensor that points to an operation. The operation is addition operation, and it has one operand as a constant 1 and another operand as tensor x. That is the second step, the graph building process. It's pretty simple. At the end of the step, we got a result of tensor y contains a pointer to an XLA node representing add, and that node also references x value and a constant value. Let's move back to our diagram for the third step, which is the syncing process, contains the root collection, the lowering process, the compilation, and the execution. After the second step, we already have a very simple computation graph that is stored in XLA tensor y. After we explicitly call the sync function, it starts to compile that code to an XLA executable. In step 11 through 13, user calls a sync function or asks for tensor values. XLA graph executor first go to the device context arena to get all the live XLA tensors, then collect all the current roots. Now we know why it's important to register the tensor to the context arena in the tensor creation process. Because at the compilation step, it's important for us to collect all the node that we currently have, and from those roots we can traverse back to their source to build the computation graph. Step 14 actually does that process. On step 14, the run post order traverses the computation graph reachable from the roots and identifies the parameters orders and determines the right traversal order for calling the lower function for each of the XLA node. In step 15 and 16, the XLA graph executor creates the lowering context and produce XLA operation roots. The lowering context maps each of the XLA node to XLA operation. In these two steps, the XLA node will be transformed to a group of XLA operation through the lowering functions that's defined for each of the operation. Then we come to step 17, which the lowering context use the generated XLA operations to generate HLO, which will be the input for the XLA runtime. On step 18, the generated HLO representation is sent to XLA runtime. Here we encounter another concept that we didn't introduce in our previous video. That is the backend implementation, right here. Backend implementation is just another layer that wraps computation client, the runtime client that actually interact with the XLA engine. Therefore, instead of calling the computation client.compile, the code will actually call XLA backend implementation.compile. The separation of the concerns keeps the runtime client specifics out of higher level graph and executor code, makes the runtime pluggable and replaceable. Because it's just a transformation layer, so I intentionally remove it from our overview. So now we know that XLA graph executor will interact with the computation client through the backend implementation. Step 19 to 21, the backend implementation uses the computation client to compile the HLO using XLA runtime. The compiled executable is returned to the backend implementation. Then we come to step 22 to 23. The compiled computation graph is executed on the device with concrete parameters. The runtime returns the device data pointers as the result. 24 to 26 is the materialization process. XLA graph executor takes the returned device data pointer, wraps them as the backend data pointer or device data, and attach them back to the XLA tensor. That is how the value of y get updated. It previously contains a computation that's represented by XLA node. after the compilation and execution, it now contains a pointer to the real value that's stored on the XLA device. When necessary, we have step 27, where fetch tensor method convert the XLA tensor back to the regular Pytorch tensor. This step 27 is triggered when it's explicitly required or when the value of tensor y is accessed. The step 27 not always happen. If the value of y is not immediately used, it won't bother to move it back to CPU or the memory on the machine. This prevents unnecessary data move and therefore saves time and resources. Okay, so this is the whole process of computation graph compilation and execution. I hope this graph can help you to have a better understanding of the whole process. This graph will be uploaded to GitHub, and I will put the link to the description of this video. Now let's move back for a brief summary of this lecture. In this lecture, we gave a lot more details about how Pytorch code is transformed to XLA executable. We discussed 5 key components and processes that make this transformation happen. They are ATEM Pytorch integration, XLA tensor, XLA node, XLA operation, and XLA computation. I hope this lecture can help in your journey of learning Pytorch XLA and build a good mental model about how Pytorch XLA works. If you have any question, please let me know in the comments. Thank you for watching. See you in the next video.